This is the campus of the Bayerische Rundfunk in Munich-Freimann. The IRT is sitting in these two buildings, and on our rooftop, somewhere over here, we have installed 7 receiving antennas which every minute record the field strength of 17 frequencies in the air. And up to now this has been done for over 4 years. Here you can see an overview where these transmitters are placed around the IRT. The measurement software that we use is written in LabVIEW, and the analysis is done in MATLAB. So let's have a look on the signal of these 3 transmitters. Rot-Jackel-Riegel, Aalen, Geisberg, and for comparison we are also looking at the transmitter Ismaning, which is just nearby Munich. We are analyzing the moving median over 60 minutes. This is an analysis of the whole year 2017. On the top we can find the stable behavior of the nearby transmitter Ismaning, but the other ones, which are far away, vary extremely over the time. For example, if you look at the month May, you can clearly see the periodic character of the field strength from day to day. Here you got a peak at 7 o'clock, at 5:15, at 6:30, and at 7:30. So it seems that in early morning the field strength are at the highest levels. The first idea could be that the temperature highly affects the field strength. Let's see. The Deutscher Wetterdienst offers temperature data for the whole year with which correlation analysis can be done. For example, the change between summer and winter is obvious, and similar to the field strength, daily changes can be seen. But let's have a look on the correlation with the field strength of the transmitter Aalen. There seems to be a relatively high negative correlation. But if you look at the distributions of temperature and field strength, there might be other effects that count more. Indeed, it is more complicated. Investigations led to the finding that it is the changing composition of the atmosphere during night and day which leads to sporadic overreaching. But sometimes the atmosphere remains in such a constellation for longer, and the electromagnetic wave gets trapped between different layers. So instead of spreading out in space, the wave moves around the Earth, which is called ducting effect. Now coming to the model, and instead of measuring, we are trying to calculate the signal strength at the receiver. A so-called 2D model takes land information along a line from receiver to transmitter as basic input data. So starting at the IRT, topographic information are to be extracted up to the transmitter. Here, for example, you can see the river Donau sampled as blue points, or the forest right here and here in green. At the end of the line, we find the transmitter Rot-Jackel-Riegel that we try to simulate. In MATLAB, the profile looks like this. On the left side is the transmitter Rot-Jackel-Riegel, and on the right side our receiving rooftop antennas. Now, according to an algorithm that is called DEGU, the most significant edges that damp the signal strength are identified. For example, this edge leads to a loss of around 9 dB, and this around 5 dB. Much more complicated it gets when it comes to modeling the field strength peaks that occur from time to time. The theory behind it is that the wave is reflected in the atmosphere and banded over the obstacles. Instead of simulating the different bending radii, a so-called K-factor is introduced, which lets the wave at a straight line, but flattens the underlying ground for the calculation with the same Deguy algorithm. So here we calculate lower losses, and less significant edges are identified. Here we get a loss of around 7 dB, and this edge leads to a loss of around 4 dB. The main task now is to bring this model of timely behavior in line with a model for different locations. This will be shown in upcoming videos.